I'll just keep my video off. I'll switch it on once when some discussion starts. Yeah, good evening, Hussein, Saifi. Please ask your question. Hussein, I read your question. See, this course has got nothing to do with administration. Uh, but if you are really interested in knowing that what are the avenues or what are the the ambits of the course, this course is quite a mathematical course which deals with advanced level condensed matter physics. And having said that, what I mean is that it is about properties of material and how material properties can be predetermined from some symmetries and from some things that are very fundamental at the fundamental level. So a lot of quantum mechanics is needed, and a lot of condensed matter physics is needed, along with some mathematical ideas. And it's mainly algebra. There is no significantly difficult mathematics that is needed, but one needs to do integration of various quantities, or one may actually needs to take derivative of very complex quantities, etc. So this gives you an idea of how the material properties can be determined. Now, going beyond this course, you have to also understand that this is some way related to quantum information and quantum computation. And how it is related, it's not, we haven't come to that part in the course, but all these robust edge states that are there in the topological insulators, these edge states, they contribute to fault tolerant quantum computation. So if you, like I have mentioned about Kitaev chain and all that, where you have Majorana physics, and these Majoranas can be suitably, combined, or rather, they can be manipulated to work as qubits. And then one can make quantum gates, such as, AND gate, NOT gate, etc. Those can be made using these Majoranas. Now, having said that, that part has not been dealt with, because that's more, even more advanced. And people without having a knowledge of this course cannot go and understand that part. So I understand that you interested in administration and science and technology, and ICT administration, I guess the ENICT Academy that you're talking about. In any case, these things, this is you can take it as a stepping stone for going into all these things that are being talked about as quantum information, quantum sensing, quantum computation, and error correction, algorithms, etc. So these are the first steps towards that, uh, towards that direction. I hope I have, explained something that is that you have asked for. Yeah, I see that. I'm reading it. Uh, mm, Hussein, I have to really think about it. It's not a very easy question. I mean, of course, there is some applications that I can think of, but uh, how, you know, because ultimately it is to do with some devising some materials, and we are really, uh, I mean, if you want the AI tools to be coming into picture, then you have to understand that how uh, the all these theories that we teach behind, they come into picture for determining material properties. So I am not very sure that how directly the content of this course can be applied to AI, ML, or something else that is related to the physics part. But as I said that, these ideas, which is one of the part of my research, is these ideas can be combined to make quantum gates. And what is meant by quantum gates is that just like your AND gate, NOT gate, and NAND gate, and all that, there are these gates that can be made. So that's one of the things that can be, thought of. Um, yeah. So I would say that you know uh, not directly, but yes, one needs more studies and more input in order to how these things can really uh, be implemented directly to AI, ML, etc. Thank you. But I gave you part of the answer, but I'm sort of really interested in thinking about the direction that you're talking about. Apart from the quantum computation that I said, that you can form qubits because these are, very robust things which do not get destroyed by disorder or some kind of impurities. So that part is that, I mean, we need to understand more of that part. We are already in the process of making some complicated gates using some Majoranas, and these Majoranas have been discussed in the context of Kitaev model in the course. So that part is still being worked upon, and it's an open question in the community that how these ideas can be directly taken over to quantum computation. A lot of research is going on, and we are also walking along that direction. Very good question, Prasoon Kumar. Uh, let me just. So the question is that about the tenfold classification, and yes, you can find more symmetries, of course, and the particle hole and chiral spans. Yes, for these, if you leave aside the crystalline symmetries, these three symmetries, namely the charge conjugation, which you're calling it as pH, chiral symmetries, and often chiral symmetry is actually a combination of inversion symmetry and maybe time reversal symmetry, or maybe particle hole symmetry, etc. So these span the entire symmetry classification. But that's not the case if you include non-hermiticity into account. If you have a non-Hermitian matrix, or if you have a non-Hermitian Hamiltonian, then you need more classification schemes. And instead of a tenfold, it becomes a 38-fold classification. But if you are ignoring all of that, you are pretty much correct that these are the only things that you have to consider. That is time reversal, particle hole, and chiral. You have to consider to form, the classification of materials which fall in either of these tenfold this thing, or 10 symmetry classes. As I said, you have to leave aside lattice or the crystal symmetries. Please ask your questions. Is Somasundaram around? Who asked this question about Berry curvature and so on? Please ask questions. Yeah, I will do that. Prasun, what bulk boundary correspondence means is that in general, it means that you don't need to consider the boundary, because boundary is a difficult concept, because then you have to terminate the system. Um, you have asked a very correct question that really bulk boundary correspondence does it mean I mean, how does one actually get it? I'll give a slightly roundabout answer to this question, the first question that you have asked. I would not talk about Thouless pumping, because this has not been taught. But if you can read Rice-Millie model and all that to understand Thouless pumping and so on. Um, uh, so this I will leave. Um, yeah. So so the bulk boundary correspondence really means that you are want to get an information about the edges through the information about the bulk. Now, the bulk Hamiltonian is periodic, which means that it has it is expressed in terms of k, or its eigenvalues and eigenvectors are expressed in terms of k, and you can calculate the quantities, the topological invariants such as Chern number or maybe Berry curvature or something like that, or say Z2 invariant, whatever is the case for, I mean, depending on the symmetry, whether you want to calculate the Z invariant or the Z2 invariant. Um, so the correspondence principle, or the bulk boundary correspondence, says that you don't need to consider explicitly the boundaries, and your bulk will give information about the boundaries. So bulk will tell you whether the boundaries have robust edge modes which are conducting in the context of this the quantum Hall systems. Now, having said that, quantum Hall system is very sort of kind of difficult to talk about, because it doesn't have any sort of translational invariance or time reversal invariance. So writing the block states for the quantum Hall system is difficult. So what Thouless, Komoto, Nightingale, and Dennis they did is that they took a sort of electronic system with the something like this periodic potentials, and they calculated the conductivity of such a system and showed that the conductivity is quantized in terms of this E square by H multiplied by an invariant which is called as a Chern number. So now this idea, having said that, this idea, suppose you can solve this quantum Hall problem in real space for a finite geometry and things like that. Then once when you do that, then this you can actually get these the same way. In the same way, the conductivity of a quantum Hall system is also quantized. Okay, but the TKNN is really for a translational invariant system. Okay, so that is an important thing. Okay. We haven't talked about much about Rice-Millie model or this Thouless pumping and all that. But you can, I mean, there is the bulk boundary correspondence plays a role when you have a pumping and when you have other, kind of time independent, I mean, time dependent driving, periodic driving, and so on and so forth. Okay. Yes, that is there. Yeah, topology is connected. As I said, that the bulk will give information about the boundaries, and the boundaries, if they have edge modes, then you have a topological system, and if they do not have edge modes, then the topology is lost. That's the whole idea. Yeah, that is, I mean, in the sense that a paramagnetic term means that there is conductivity without an electric field, which is not a relevant thing here. I mean, you're not talking about a term without an electric field. So that is called as the paramagnetic, dependent of the magnet. Say, for example, Ohm's law. So Ohm's law is like V equal to IR. So you sort of apply a voltage and then you get a current. This is like getting a current without application of a voltage, which automatically comes because of the structure of the form. So that's how it is called as paramagnetic term. That term is not important, which was dropped later. Please ask your questions. Come in. Yeah, please ask questions. Yeah, good afternoon, Rahul. Uh, uh, First of all, you should have prepared for final exam. You should have gone through the lecture notes. It would be improper if I say that if you only focus on assignment question of all weeks. But yes, you should pass with all the assignment questions because there are some questions which are very close to what we have asked in the assignments. But on the other hand, you should also have a look at the lecture notes. There could be questions directly from the lecture notes. I hope that answers your question. But you should study, I mean, in a course which is advanced level course, you should study because in order to satisfactorily answer all your assignment questions, you need to know the the solutions, or rather how they come. And there could be some questions which require you to, satisfactorily and I mean understand, not only remember but also understand. But having said that, I think you should pass if that is what you want. Sorry, I am not sure whether I have answered your question. I said, but my mic was off. It's a 3-year duration. Yes, the exam pattern, as I said, is a short answer type, either numerical answers or the answers will comprise of short expressions for some quantities or some parameter that we ask for, or maybe short explanation. And I don't remember how many 2 marks or 1 mark question. Okay, that I don't remember. Uh, I answered your question, Rahul. Is that fine? I mean, my answer was audible, right? Okay. Thank you. Is there any other question? We'll wait for a few minutes. There was a question called as how do you calculate Berry curvature? So a short answer to that would be, you take a Hamiltonian, and most of the time we have talked about 2 by 2 Hamiltonian or maybe 4 by 4. 4 by 4 is slightly more difficult, but let's say we have a 2 by 2 Hamiltonian, you solve it, you get a 2 eigenvalues, and each eigenvalue will correspond to a 2-column vector. I mean, 1 cross 2 column vectors. You treat them as block vectors and calculate the expectation value of the velocity term. Uh, so it's like UK del K of UK. And this quantity is related to the Berry curvature. Then you integrate it over the Brillouin zone, and that will give you the Chern number or the topological invariant. And the time reversal symmetry or the symmetries actually protect the edge modes. And these symmetries are specific. The symmetries are possessed by the entire system, but the symmetries, when you find that, the behavior of the edge modes or the surface modes or the corner modes, depending on what kind of situation you're talking about, these behavior of the corner modes, if they are different than the bulk, then these fundamental symmetries, they actually, you know, protect the boundaries or the behavior of the boundaries of the surface modes. This was one of the questions from some learner called Somasundaram, who probably did not appear here or not present here, but that is the question. So, Queen, if there are no question in 1 or 2 minutes, we can wind up. Queen, is it the last one, live interaction? All right. I guess all right then. We are done with the time as well. So all the best to all the learners for doing well in the exam. I hope this course has given you a feeling that what the state of the art topics in condensed matter physics is. And I hope that some of you would do, PhD in physics and in particular condensed matter physics, and you would have a first-hand experience of what I wanted to talk. And there's still no good textbook on this. I have written a book. You can have a look at it. It's called Topology and Condensed Matter Physics, very similar to or rather the same as the title of this course. and I have used a lot of input while teaching this course during writing of the book. So hopefully it will come to of use. Thank you, Quinn. Thank you very much.